Okay, thank you for coming, Yong. Let's start the section for today. So today, I'm gonna solve some related questions of homework 4. So this is our first agenda for today. Secondly, I'm gonna go over some basic concepts of game theory. Okay, so these are two things that I'm going to do today. Okay, so unfortunately, I was very ambitious when I was preparing this note. I was going to cover question 1, question 2 of the homework, and then also cover game theory. So I found out that this is impossible. So in the previous section, I found out this is impossible. So I'm gonna not cover question 2 today. However, I'm gonna give you the answer key for this one, for this question. And then, yeah, I'll try to solve question 1 and question 3. I'm sorry. Yeah, so question A of question 1 and question C of question 1, and then I'm also gonna go through the game theory. Any questions? Okay. Or maybe if you have any other question that you want to discuss, then I can also go for that one for you. So I can also go over question 2 if you want. But if you have no other objections, let me move on. Let me solve from question 1. Okay, so far so good, thank you. So assume beta equals to 0.5 and delta equals to 1. And then we have this payoff stream of payoffs 4, 7, 10, 18. And then we're gonna see how naive agent and sophisticated agent would act differently. So this is the big picture. So let me move on. Okay, so we are gonna solve this problem using backward induction. So first, assume that the agent is naive. In the final period, he will say yes. So he will yes to see the movie. So let me phrase this question as watching the movie. Yes, 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 yes. In the final period. So the final period is a bit trivial. So let me just put y's first. And then let me solve from period 3. Okay. So his plan will be yes in period 3. So what's the plan? If he is doing this for the plan, he's thinking that his beta equals to 1, which is wrong. And he's going to compare 10, which is the immediate benefit, the benefit now, versus 18 times 1. Nothing is discounted. He's using the wrong discount factor, which is 1. Okay. So this is 18. So we can see that this value is larger. So the benefit for the future is larger. So he's not gonna watch the movie now in his plan. Oh, I'm sorry for making a mistake. So this one should be no n. Okay. Any questions so far? Oh, if you have any questions, just let me anytime. Okay, you can stop me anytime if you have any questions. Okay, thank you. Yeah, thank you. No questions so far. Now, suppose that this was an actual choice. Then we are comparing 10 versus 18 point to 0.5, which is the beta. And also we have to multiply with delta. So this is 18.5, we have 9. Now the left-hand side is larger, which is the benefit of now, okay? So we can see that actually he's going to say yes. Okay, any questions? Okay, thank you. Yeah. And then let me just copy and paste the plan from above. So let me just put no here. And then let's see what he's going to do based on his plan. If this was a plan, then we're comparing 7 versus the first time that he's going to say yes in his mind is the 4th period. Okay, so we're just comparing the best option, 18, with 7. So we can see that the right-hand side is larger. So he's going to say no according to his plan. Let me use color black. And then if beta was 0.5, so if I'm looking at his actual choice, then we are comparing 7 versus, now we need to compare this with also the first time that he says yes in his plans, and then it is 18. So what is different here is that we need to multiply with 0.5 times 0.5, which is 9. And then we can see that this number is larger. So he's also saying no here. No. And then no. This one should be no. Oh, I'm sorry. Let me use color black. No, no. Oh, I'm sorry for making a mistake. There's no actual choice of the naive agent is just copy and paste from here. So this should be yes. Oh, I'm sorry for making confusions. Yeah. Okay. And then what is his choice in period 1? So let me use color red to copy and paste what we did so far, and then just put the final dot here. So his actual choice is obtained by using beta equals to 0.5. His benefit right now, the immediate benefit right now is 4. We compare that with 18. So we just track his plans and then look at where the first y appears, okay, or the best option that he can get. This was 18 times 0.5, which is 9. Long story short, 9 is better than 4, so he will say no here. No, okay. Does this make sense? Thank you.
So just to clarify, like the part plan is basically what is basically the case when the beta is equal to 1, right?
Yes.
Okay,
So,
I got it.
Yeah, thank you. Yeah, so thank you for the clarification. Yeah, so when we consider the plans, he's thinking that his beta equals to 1.
Okay.
But when he's making actual choice, then the beta, now then we need to use the actual beta, which is 0.5. Does that make sense?
Thank you for clarification.
Thank you. Yeah, thank you for the question. Very good. Now we use sophisticated agent. So the table looked different because in here, the plan is the same as his actual choice. So there we don't need to differentiate. We don't need to distinguish the plan and his actual choice. Okay. So for the sophisticated agent, he's saying yes, 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 yes. And then we also use the backward induction. So in period 3, okay, so he's comparing beta equals to 0.5, okay? Regardless of plan or actual choice, he's always solving the correct problem. We compare this 10 with 18 times 0.5 times 1 for the discount factor, delta. So his utility in the future will be 9. And we can see that 10 is larger than 9. So he will watch the movie, okay? And then let me just copy and paste for the future users. And then let me focus on this cell of the table here. So for this one, beta equals to 0.5. 7 is the utility for now, watching the movie now, versus now, if I don't watch the movie, then he's gonna watch the movie in the third period. So we have 10 times 0.5, which is 5. So utility of watching movie now is larger than watching the movie in the future. So yes, he's gonna watch the movie now. Yeah, so I know that Yi-Hong already know this very well based on what he explained in our main lecture. But let me still go over the last step, the period one. So it can be a bit tedious, but let me finish this example. So for the sophisticated agent, beta equals to 0.5. And then 4 is the immediate reward, immediate payoff. Just compare this with the first time that he watches the movie in the future, which is the period 2. So we compare 4 with 7 times 0.5, which is 3.5. So 4 is larger than 3.5. So he's gonna watch the movie in period 1. So these blue boxes are the answers for the naive agent and the sophisticated agent. Okay, so now versus future. Now versus future. Now, any questions? Okay, so if this looks okay. So I'm gonna finish these cells after this section, and then let me post on Canvas. This is an interesting example where we have negative values here. So in the original paper of Odonok et al., let me write Odonok and Rabin. The original paper is 1999, published in American Economic Review. Okay, this is cited like 5,000 times. Okay, so one of the most influential paper in this area, maybe in whole behavioral economics. So they give 2 examples: benefits, like the positive values here, and costs, like this. So let us see this interesting case, and then finish question 1. Okay. The way of solving question is exactly the same. In the note that we have the beta equals to 0.7 here. Let me first put y for the period 4, which is trivial. And then let me go to period 3. And then the way that I phrase this question is like choosing when to visit the dentist. And you can say that if you don't visit the dentist now, then your pain will increase. Okay, so if you visit dentist 1 month later, your pain will be enormous, like -13. Okay, so in period 3 for the naive agent, let's see what he's going to do. He's thinking that if I don't visit dentist now, then my pain is -11, versus if I don't visit dentist now, then I need to visit dentist tomorrow or period 4, and then my pain is -13. I don't need to discount this because this is happening in the naive agent's mind. Okay, so -11 is larger. So yes, my naive agent is thinking that I'm gonna visit the dentist. And then let's see what happens in reality for the consistency. Let me put the discount factor that I used for this one. And then in reality, beta equals to 0.7. So I need to compare -11 versus -13 times times 0.7, which is -9.1, I guess. And then we can see that this number is larger, 9.1. -9.1 is larger. So the naive agent is not gonna visit the dentist. Does this make sense? Okay. Then let me copy and paste the answers from the above. Then let me go to period 2. In period 2, if this was a plan, then using backward induction, we can see that -9, we're comparing -9 with -11 time, -11, done. And then we can see that this number is larger. So in his plan, according to his plan, he's gonna visit the dentist in period 2. And then if this was not a plan, the actual choice, we are comparing -9 versus, he's thinking that he's gonna visit the dentist in period 3, okay? So it should be -11 times 0.7, which is -7.7. So this is larger. So we can see that he's not gonna visit the dentist. Oops, black color. Not, yeah, not up. What is this? Not, okay. Does this make sense? Okay. Yes, question.
Yeah, I know this is a case for naive agents, right? So
Mhm.
do we need to actually consider the case at like week period 4? Because right now we only cares about like -9 or -11. I think it's also worth it to care about like the case when the utility is -13, right?
You mean we need to care about the case here, right?
Yeah,
-13.
because this is
Yes.
naive agent, right?
Yeah, so the naive agent is thinking like he's choosing the best option available in the future.
Mm-hmm.
But this is a negative value. So the best one happens, which is near to now. So,
Okay.
so naive agent will be comparing -9 with -11. Oh yeah, but you're right. Yeah, -13 is also considered, but it
Mm-hmm.
is discarded in the future because naive agent, he's thinking that I'm gonna visit the dentist as earliest as possible. So -13 was considered here, but it was discarded. Does that make sense?
Mm-hmm. Makes sense.
Okay. And then let me go to period 1. Beta equals to 0.7. So we are comparing -7, which is the pain now, versus he's thinking that if I don't go to the dentist now, then June is gonna visit dentist in next week, which is wrong. You're gonna visit dentist 1 month later after your tooth gets really screwed. But according to my wrong plan, I'm thinking that my pain is -9. And then I discount that with 0.7, which is -6.3. What happens is that this one is larger, right? So I'm not gonna go to the dentist. Black color. Yeah. Okay, yeah. And then for the sophisticated agent, we do the same thing using backward induction. Let's see. No. I'm sorry, yes. Okay. And then here I compare -11 versus -13 times 0.7. We did the computation above, -9.1. So we can see that this number is larger. So he will say no. So he's not going to dentist in period 3. Okay. Let me copy and paste what we did above. Let me go to period 2, where beta equals to 0. Beta will be 0.7 for all of the examples for the sophisticated agent. So let me just not write that here. I'm just comparing -9 versus minus 13. So he's correctly thinking that, yes, I'm not going to go to dentist in period 3. So my pain, actual pain, is minus 13 times. Discount that with 0.7, which is minus 9.1, I guess. So this number is larger. So I might rather go to dentist this week or this period. So let me put yes for this one. Yes for this one. Now, in period 1, I'm comparing minus 7 versus, if I don't go to the dentist, then I'm going to visit dentist next week, minus 9 times 0.7. What happens? Minus 6.3. So pain today is larger than pain tomorrow. So I'm not going to visit dentist right now. So I'll put no here. Look at this. These purple boxes are the answers. No, 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 Y for the naive agent. No Y for the sophisticated agent. The sophisticated agent, based on his true belief, he's going to visit dentist sooner than the naive agent. Naive agent will end up visiting dentist 1 month later. For the sophisticated agent, yeah, he's visiting dentist 2nd week. So in any cases, sophisticated agent is reaping the benefits earlier. So this was phrased as benefits, reaping benefits earlier. But he's also, when facing costs, he's also kind of acting earlier against the costs. So in this case, he was better off. Any questions? Okay. So when facing benefits, sophisticated agent was kind of screwed, worse off. But when facing costs, he was better off. Anyway, so this was the intuition. This was the nice implication coming from O'Donoghue-Rabin, 1999. Now going to game theory. So our professor was asking me to go over a review of the game theory for the basic concepts. So for the remaining 20 minutes or so, let me give you a review of game theory based on this simple 2x2 game. So why is it called 2x2? 2x2. So we have two twos here. First two stands for the number of players. Second two for number of strategies or options or choices available. So if you see this table, let me just erase this, which is not very important. You can see that there are 2 players, 2 idiots, 1 and 2. They can go straight, swerve, go straight, or swerve. Okay. So this game is, this has a name. This is called the chicken game. Yeah, so let's see who is a chicken. So if they go straight, so they are driving 2 cars like this, idiot 1 and 2 each. If they go straight, the car gets smashed and both go to the hospital. Okay. So minus 100 is their utility in this case. If they swerve, suppose that idiot 1 goes straight, idiot 2 defer this challenge, then idiot 2 becomes, then idiot 1 is the brave guy. He gets all the honors, if there's any. And then his utility will be 100. Minus 2, being a coward, he got really high mental damage. His utility will be minus 200. So this is so this is like how this example works. Okay. Now, so the intuitively how this example works is easy. But let me but to make a communication, to make an academic communication, let me go through some definitions that we use. Okay, using this example. So when we say players, it is players making strategic interactions in this game. So in here, we have 2 players, idiot 1, idiot 2, okay? So we label, so this is a set of players, and then we use label I for players. And then strategies in the simple case is something like set of options that is available, or set of what I can choose from. So in here, the choices in this case was the same for player 1 and player 2. They can either go straight or either swerve, but it doesn't have to be the same, right? Because if idiot 2 can also have another option called cops, then the set of strategies for idiot 2 might not be the same of the set of strategy for idiot 1. So it doesn't have to be the same, but in this simple example, it is the same. In this simple example, it's the same. Now, what is the difference between strategy and strategy profile that I'm going to explain now? So this set of strategy profile is like combining strategies of all the players, okay? So this strategy is for each player. This strategy profile is for the entire game, okay? So the set of all possible strategy profile S looks like this in this game, in this example. It can be go straight, go straight, go straight, swerve, swerve, go straight, swerve, swerve. So the first element stands for the strategy of the first player. The second element, this one, stands for the strategy of the second player. Any questions? Okay. They sound similar, but this one is for each player. Profile is for entire game. What all players have chosen. So it's combining strategies. Outcome intuitively is just what can happen from this game. Okay, so all of these are outcomes. Okay? But you know that if I made this example like minus 200 and 100 here, then actually there are 3 outcomes in this game, because this one and this one will be the same. So in this case, we have 4 outcomes, but it doesn't have to be 4. So even if it is 2x2 game, there can be 1 outcome, 2 outcomes, 3 outcome, or 4 outcome. The way of denoting outcomes differs by economist by economist. Let me just use simple notation, just writing all the payoffs like this. But sometimes some people write O1, O2, O3, O4. So it doesn't have to be my way, but yeah. So there are many ways of writing outcomes. So key thing is that even in 2x2 games, there can be 1 outcome. It doesn't have to be 4 outcomes. Any questions about the outcome? Okay, good. And payoff is also easy to understand. So payoff is a function that maps outcome to utility. Okay. So payoff, this one, is a payoff function for player 1. So the sub-index 1 is for players. So 1 means this is the payoff for player 1. So if I have an outcome A and B, I'll give A, I'll associate A for the payoff of player 1. Okay. So simply, if this was pi 1 minus 100 minus 100, then the first player's payoff is the first element minus 100. So this is what it is saying. Any questions for the payoffs? Okay. Now we are ready to state what the best response is. So in plain English, best response is saying what my best strategy is based on my opponent's strategy. So I wrote in this dirty math here, but it is best understood by using the example. So let me just go back to this table and then see what the best response is for all the possible cases. I'm going to use orange to denote best response. So BR is the best response of player 1. P1 means player 1. I didn't use blue, so blue. For the best response of player 2. Okay. So in the space example, let's see what the best responses are. Let me start with best response of player 1. If idiot 2 goes straight, then what is my best response? I need to focus on the first element, which is the payoff of the player 1. Do I go straight or do I swerve? Up or down? Up.
We go straight.
We go straight, very good. So I promise to use color, this one, orange. So let me put a dot here to denote the best response of idiot 1. And then this concept is for strategy by strategy. So we need to also specify what the idiot 1 should do if idiot 2 swerves. Okay, which one is larger? Go straight or swerve?
Still go straight.
Very good. Yes, still go straight. So this is the best response, given that the strategy of idiot 2 is swerve. Very good. So we can do it in the opposite way. The best response of player 2 using color blue. So suppose that idiot 1 goes straight. So we're focusing on this row here. Then what should idiot 2 do? What is the best response?
Still go straight.
Still go straight, very good. And if the idiot 1 swerves, which one gives the highest utility, or higher utility?
Go straight.
Go straight. Very good, go straight. Okay. So we can denote best responses in the table like this, but sometimes we can also denote best responses as a function. Best response is a function for each players. And I think the professor would use the notation BR, best response of so this index, subindex is for the players. Argument, so this is a function. The input of this function is the opponent's strategy. Output is my best strategy. So the domain of this function is a strategy, but it is opponent's strategy. Range of this function is a strategy, but my strategy. Okay, because this is my best response. So if professor uses this notation, this is essentially the same as making dots in this table, because this is also a function, right? Based on this go straight of idiot 2, my output, my best response is go straight. So either notation is fine. So this one that I give you here might be useful in the exam, but when you make a communication in the class, then I think you might be using this function notation, but they're essentially the same. And based on this definition of best response, now we are ready to define what the Nash equilibrium is. Nash equilibrium in one sentence is a mutual best response, okay? So what is Nash equilibrium defined upon? It is defined upon a strategy profile, okay? So focusing on all of the strategies of all the players, it is a Nash equilibrium if player 1, if S1 is a best response based on S2, and if S2 is a best response of player 2 based on S1. So in a loose sense, we sometimes call it as a mutual best response. Okay. So this is how we define. Yeah.
So to clarify, like the Nash equilibrium is it can be also interpreted as a point that like both players cannot get higher benefits or higher profit by moving to other options, right?
Very good, very good. Okay. So yeah, so I think you were explaining no incentive to deviate. Yes, right, very good. So there should be no incentive to deviate from the Nash equilibrium. Very good. Because they were the best responses. Very good. You're correct. What is the Nash equilibrium of the game above? Let me copy and paste the game. Copy. Paste image. Okay, very good. If there are two dots, then it is the best. It is the Nash equilibrium. Pink one. This one. Go straight is the NE, Nash equilibrium of this game. So just put the dots in the table, and then if you have all the dots in one cell, then those are the Nash equilibrium. It doesn't have to be unique. Note that doesn't have to be unique. In some of the game, we have two Nash equilibrium. Of course, in a trivial example where payoffs are all zeros like this, then there are four Nash equilibriums. Okay, so it doesn't have to be one, doesn't have to be two. There can be many, many Nash equilibriums. Any questions? And then also there are some efficient way of finding Nash equilibrium based on weak or strictly dominant strategies. So a strategy is a weakly dominant strategy for player one. In simple language, if there's no better option than S1, then it is a weakly dominant strategy. Okay, if it is a strictly dominant, strategy, then it is strictly better than all other options for me. Okay, so this is what it means. There's dirty math here, but it's just saying that it is giving me the best payoff. Okay, compared to other options. Okay, it is giving me strictly better options compared to other options. This is just what I wrote here. Okay? So understanding English is much better than this dirty math. So what is the weakly strictly dominant strategies for player 1 and 2 of the game above? Can you find what the weakly dominant strategy is for player 1?
I think going straight is the dominant strategy.
Very good, very good.
And I think it's a strictly dominant strategy rather than weakly dominant strategy.
Very good, very good. Yes. So for player 1, yes, as you said, going straight is, yes, it is both weakly and both strictly dominant.
So just to clarify, it like when we say something, when we say a strategy is strictly dominant strategy, so it also satisfies that it is a weakly dominant strategy, right?
Very good, very good. Yeah, in any cases, if it is a strict dominant strategy, then it is also a weak dominant strategy. Yeah.
So do we have to write both of them at the same time?
You mean in the exam?
Yeah.
I think we don't need to. So if you just write it is a strictly dominant strategy, then yeah, it will be automatically implying that it is a weakly dominant.
Thank you.
Yeah. So we can just take that as given. Very good. Yeah. So and then also for idiot 2, yeah, is the going straight will be the weakly and strictly dominant weakly and strictly dominant strategy. Okay, so I think this is what I wanted to explain for today. We have another example. So this is a prisoner's dilemma. So we can also try to find the best response of prisoner 1 and prisoner 2. So if the prisoner 2 is silent, then my best response is this one, to betray. And if prisoner 2 betrays, then my best response is this one, also betray. And then for player 2, if I use color blue, if the player 1 becomes silent, then my best response is to betray. If the player 1 betrays, then I also betray, like this. Okay, so this is a Nash equilibrium in this game. Yeah. Because we have a mutual response, a mutual best response in here. I think I tweaked the original prisoner's dilemma game, so it can be different. I may have different Nash equilibrium from the original game. Yeah, so I think we will see the original game in the class. Okay. And then, yeah, we have also weakly and strictly dominant strategies here. So it is betraying for player 1 and betraying for a prisoner 2. Yeah. Because if I move down, you can see that if I focus on these 4 circles here, I always get higher utility if I go down. So betraying is the dominant, both strictly and weakly dominant strategy. Okay. Okay, so this is what I wanted to cover today. Thank you for coming. See you next week.
Okay.
Let me stop recording. Do you have any question?